in fluid dynamics, you're going to run into Reynolds number. And this is a very well known kind of equation that you have. There's various variations of this particular equation, so it depends on how deep you're going to go. This is one of the simpler ones that you have, but they all obviously kind of are after exactly the same thing, which is when you do have a tube or a pipe and you have a fluid flowing in that pipe, we want to be able to see when that particular flow is laminar, okay, or if it's turbulent. Now, the distinction between laminar and turbulent is not super difficult, although I will not necessarily talk about it too much in this video. If you want to know a little bit more, okay, I'll put up a link above there for an introduction to those flows. So in here, okay, all I want to be able to do is just kind of give you a gist between laminar and turbulent flow, and then finding out what this number exactly does for us. Okay, so first of all, if you take a pipe, this is always going to be assuming that we're kind of flowing in the horizontal. So let me take a pipe, okay, or some kind of a tube that I have. So I'm going to create this out, and we have a fluid which is going to be flowing in this particular pipe that you have. Okay, so say it's flowing in, and ideally, okay, as this fluid flow, we would want it to be laminar. So basically, kind of a nice straight flow in between. Okay, so this is typically for viscous fluids. Okay, so there's some viscosity that we have, and I'll talk about all of those kind of variables and coefficients that you have, okay, up above in that formula. But you have these layers, okay, in this, or layer-like flow in between, where you have these particular fluids kind of flowing in, okay, and they're flowing the fastest kind of in the middle, okay, and then they're moving along and flowing not as fast, okay, as you get closer and closer to the edges. And in fact, as you get super close to the edges, it pretty much slows down to zero. Okay, so this is because of the viscosity that you have. So very often this will be dedicated, as you can see there, as I'm kind of creating it on the screen. So this is very much like a laminar flow, where, you know, the fluids are flowing in these kind of layer-like, okay, and they're not really interacting in between themselves as much, okay, or very little, and they're nicely flowing through the pipe. Now, if you're going to be increasing the speed of this flow, right? So this is the V that you see in here. So this is actually the speed, okay, of this particular fluid. So as it gets faster and faster and faster, you might start to think that, is there some kind of an interaction that's going to happen between all the different layers that you have of this fluid as it's flowing by? Or is it just simply nicely just kind of flowing along, okay, and then passing by? Okay, well, so it turns out that as you do make your actual speed faster and faster, you might run into the problem that this laminar, kind of this nice, beautiful flow that we have, is going to turn a little bit more kind of chaotic, and it's not going to be as smooth, and it's going to be turbulent, okay, within. And what you're going to see, so very often, you know, this is kind of designated in this way, you know, where the fluid kind of starts to overlap in between, and you know, you can see there that it's kind of going all the way around, but of course it's still being pushed, okay, in this direction. It's just not as nice. Now, this is very easy for us to kind of imagine, you know, if you had something in here where there was some kind of a blockage, okay, so maybe partial blockage like this, well, then you know that the fluid is going to hit that, and then it's going to, you know, hit the other layers, and it's going to start to kind of be turbulent throughout. So this is very easy to understand when we do have these narrowings, blockages, okay, rough-ins, okay, impurities that are happening within the pipes. So that can happen. But for Reynolds number, this is not so much about these particular blockages. The assumption is that it is actually flowing. There's not necessarily much of these blockages or impurities. It is just the fact that you're now trying to speed up this fluid, and it goes faster and faster. And this, of course, may happen because you might have changes in pressure, right? So the actual volume flow will change as well. And that, you know, you may remember, okay, as well with regards to that, because of Poiseuille's law, which I can put up a link up above there, which talks about the volume flow rate when you do have changes in pressure, okay, at various points. So This is very much, okay, so within here, a laminar flow, and this is very much kind of turbulent flow. And we want to know kind of what is the onset, so when does this exactly happen? And Reynolds number nicely captures this for us. So what does this Reynolds number do, you know, and how can we interpret it? Well, we can do it in this way. So first of all, this is a unitless number. So if you would substitute all of these inside here, you will notice that the units are going to cancel each other off. So there's no unit. So it's just literally a number that we have. Now, what are all of these? So this is our density of the fluid that we have. So we're assuming that it's pretty much incompressible. Okay, so it's a fluid where the density pretty much stays the same. So this doesn't change. This actual D right here, this is the diameter. So that's going to be the diameter over here. So sometimes, you know, this might be changed over and just simply put this 2 times the radius. And that also is going to be another way that you can see this. Now, I'm going to also put, you know, links in the description. This isn't something that I've invented or that I, you know about. It's something that I've learned. So I definitely do want to give credit. Okay, so I'll put up the description notes, and I'll put several links, which hopefully, if anyone is interested, you know, you can dive in a little bit deeper. In particular, you know, one which I really like because it's completely free and it has a full textbook is the OpenStax. Okay, so you can look at there. So coming back to here, so again, so this is density, okay, this right here, this D is the diameter of your pipe. This is the viscosity, so this is the actual coefficient of viscosity of whatever fluid you have. And again, so if you notice the density, you know, the actual pipe's diameter and the viscosity, so the coefficient, they don't really change. And so really the only thing that changes is this velocity, and this is the velocity, you know, meters per second that you're going to have in the particular fluid. So if it gets higher and higher, you notice that this number is going to get higher and higher because these are proportional to each other. And so because of that proportionality, you know, that number as it gets bigger and bigger is going to be kind of careful for us that we're going to run into this. So just for yourself and so that you kind of know, well, it turns out that if you do take the Reynolds number and it turns out that it's kind of less than about 2000, so when you do the computation, in this cases, then what we typically will observe is that this is going to be a laminar flow. So it's going to be this nice flowing through the pipe. If it turns out that your number is actually kind of above 3000 right here, then this is going to be pretty much turbulent, okay? So that's what you're going to observe. And now, if it is anywhere, so if it's kind of between, you know, 2000, and if it's under 3000, then this might actually oscillate between one or the other. Laminar or turbulence just depends on kind of the impurities that you have within your tube or your pipe. So we can't really fully out tell. We may need a little bit more information what's happening with regards to our pipe. But if we are, you know, kind of under 2000 or well under 2000, you know, we're confident that it's going to be laminar. And if it's over 3000, you know, we're again a little bit more confident that it's going to be turbulent flow that you're going to have. So a little bit more chaotic. So let's take a look at an example on how to apply this particular formula. So I'm going to just take it. All right, so here it is. So here's the example that we want to be able to work through. So let's walk ourselves through this. So we have water and it is flowing through a very thin needle-like tube of diameter 0.25 millimeters. I'm going to start writing these things down for myself. So given pieces of information, you can certainly draw it, okay, if it makes it easier on you. You know, so you can certainly draw this out. Okay, so let me just draw, you know, kind of like a pipe looking. So this is the diameter, so that would have been the D, so that's from here to here. That diameter is, so it's very tiny, 0.25 millimeters. It is experiencing a volume flow, so notice that the volume flow through this, okay, so that is going to be, this is the volume flow rate. This isn't, we're going to need to find out what the speed is, but if we have the actual diameter, then we obviously have the radius, so we can find the cross-sectional area of this. So just a reminder to everybody who's watching, you know, the volume flow rate, one way to find it, especially if you do have the volume flow rate given, okay, and then so this is just cross-sectional area times V, Okay, so for us, so this is going to be pi, r squared multiplied by v. And I'm going to need to find out what this v is in order to find the Reynolds number. So they're telling us that this flow is 0.22 centimeters cubed per second. All right, so we have centimeters cubed per second. So we'll find out what this speed is in just a moment. So what else do they give us? The coefficient, okay, of viscosity, so that's going to be this right there, is 1 times 10 to the negative 3 Pascal seconds. All right, so let's write that down. So I'm going to just put that right in here, actually. So that's 1 times 10 to the negative 3 Pascal seconds. This is actually all in metric standard units, although the other things have not been up to this point. And then density of water, well, that one is easy. So 1 gram per milliliter, which is the same thing, by the way. 1 gram per milliliter is the same thing as basically 1,000 kilograms per meter cubed. Okay, so if you're thinking back of densities, I can put up a link up above there, okay, if you've forgotten about that. So I'm not going to go into details on those. Okay, so within here, I'm just going to write down that the density, okay, so this is 1,000 kilograms per meter cubed, and that is exactly the same thing as saying, so they actually wrote it, I think, in this way, 1 gram, okay, per milliliter, or that is per centimeter cubed, right? So this is for water. We're assuming at regular kind of temperature in here. Then find the Reynolds number to 3 significant figures and predict if the flow is laminar or turbulent. Okay, so let's take a look. So we pretty much have everything, right? So we have eta, we have our density, we have our diameter, right? So really we just don't have the speed, but we can certainly find what that speed is in here. So let's do that. Okay, so within here, so I'm going to take the information which is given, and I'm going to just take this right here, okay, copy, duplicate it, and let's do that first. Okay, so now, again, this is all up to you, right? So you can literally change everything to SI units if you want to, or you can work with, centimeters for the moment, okay, and then change it back to meters. So maybe that's what I'll do. So they give me the radius right here. So that particular radius is going to be, so this is 0.25 millimeters, so the radius is going to be divided by 2, because that's the diameter, okay, you divide the diameter by 2, so that's going to give us, okay, what we need. Now if we want it in centimeters, so from millimeters to centimeters, okay, so that's going to be just 1 flop, okay, of the decimal. So there you have it. So that's what this is going to be in terms of centimeters, so from milli, okay, back to centi, right? So we're kind of just shifting over to the left. So there you have it. So now it's in centimeters, and this is also in centimeters, which is fine. So that means that my speed is going to be in centimeters per second. Okay, so if I do that, so let's put this 0.22. This is just pi, my r. So this, I'm going to just substitute this back in here. Divided by 2. This is squared. And then this is going to give me my v. All right. So we're going to isolate for this. Okay. So let's do that. I'm going to take out my calculator. Okay. And we'll find out what we get. All right. So there you have it. I mean, this is pretty quick. Okay. That it's kind of moving along. So I got my centimeters per second, and then I can convert it back. You can keep, as many decimals as you can in there. So this is actually what we would have. And so if you wanted to take this answer and keep it, there's always 100 centimeters in a meter, so 4.4818, etc. So I'll just leave it there for the moment so that I have it, and then I can use it. So that's my v. And now if you want to plug everything back into this equation, so this right here, so we need our density, now we have our speed, okay, we have our diameter in here, and then we have this right here, which is our coefficient of viscosity. So all of these are actually given. So let me take out the calculator. So here's my speed, okay, that I have. I'm going to be multiplying it by, so the density. So I'm just kind of going one by one. So I'm going this times this times this, okay. So let's do that. So my density is 1000, 1, 2, 3. And then I'm going to multiply by the diameter. So the diameter is 0.25 millimeters, so just be careful, change it back to meters. So for those who are kind of keeping track, so this is going to be 0 point, and we're going to have 0.00025 meters. Okay, so I'm going to multiply this 0 point and 12325. Okay, so that is your numerator. So that's all of that right there. And I'll take this and then divide it by our actual viscosity. So within here, and our viscosity, so as you can see there, so that's right here. Okay, so I can do that directly. I'm actually going to write it out instead of scientific notation. And I'll just put it directly into decimal. So that's what you have there. And there is our Reynolds number. Okay, so we have, so approximately, we have 1, 1, 2, 0. So it says the 3 significant figures, so I'll just leave it at that. And what does that mean? Well, it's definitely less than 2000, so it looks like this flow would have still been laminar. And that's how actually you can apply this particular equation and find the Reynolds number. It's not very difficult to be able to do that, as long as you're comfortable with your units, okay, your conversions, keeping things in SI units, being consistent on those. And that is it, okay, that I have here for this one. It's one of the, I guess, final videos, at least for the moment, on fluid dynamics. Okay, thanks for watching. See you in future videos. Bye, everybody.